Okay, so we're just having a discussion kind of before I got things going here in class on the Connect homework on number 9 and 10, specifically 9B and then I think it's 9 or 10B and C parts of it. Don't worry about doing it. I'll end up giving you guys kind of credit for it. Goes a little bit further than what I want to do with those log models. I want to kind of take a different direction, which we'll kind of see today. So we'll start off with the only type of log questions or we need to understand, and we'll kind of move a little bit more into what I want to transition to kind of after break, which after break, I will kind of just still be recording these lectures at 1 o'clock on if you want to join in the Zoom. That first week will be some new material or some more discussion, and then kind of the second week, I'll post some practice exams after Thanksgiving, and then that second week after Thanksgiving, we'll just be doing kind of review problems for the final, which will be kind of like we've had the other two. It'll be probably a little bit longer, like a 72-hour period in which you can take it during that finals week. And I'll make sure it kind of lines up with the time slot that would have existed for this class if we were in person. But you'll have some flexibility with that. So that being said, are there any other questions before we kind of jump into it? Okay, and I'll post an announcement about that Connect assignment, those problems as well. So we'll start out, since we kind of had this discussion, I'll kind of start out with that, and then we'll kind of jump into the slides later. So the very last slide that I posted kind of this week looks at kind of the specification. So it's kind of where we left off last week. And I kind of showed you a GPA SAT model pretty quick at the end of class, right? So on question 8 in the Connect assignment, someone's asking, he says you can't do a log or a level log specification in Excel. You know, and I specifically kind of showed you how we do that last class, so they're kind of lying to you. So the reason why it says you can't do it is usually, like if I didn't have these two columns, there's no way in that data analysis kind of tool, which hopefully all of you have at least been able to kind of figure out how to get that added in your computer at this point. If not, please do that soon so we can kind of troubleshoot any issues with it. There's no option where if I just select the original levels of the variable that I can change it to a log. What I can do, right, is create these new variables or these new columns where I just take the natural log of weight. Oops, I don't want to do that. Hold on, let me move this guy out of the way. Take the natural log. All right, the cell's being ordered to, okay. So I'll take the natural log of weight, hit enter. I can then copy that down for every single cell by double left clicking once I get this little black plus sign. And then it kind of just takes the natural log of every observation I have for weight. Here it's kind of nice because height and weight are right next to each other, so I don't even really have to kind of type this in, but I could just do the natural log of height, double left click once I get this black kind of plus sign. Now I have these log versions of the variable. So if I wanted to do a log model here, Zoom will get out of the way there. I'll go to my regression tool, my Y variable. Let's say I'm going to try to predict weight based off someone's height, but I don't think that level changes matter. I think that percentage changes matter. So I select that weight variable. It's my Y variable, the log of weight, sorry. And then as my X variable, scroll up here, I'm going to select the log of my height that I created. I selected the labels, so I better make sure I click that. Right? Otherwise, it kind of treats them as some weird number and it'll throw off my results. I'm going to put it on a new worksheet. And now I've got kind of these log results, right? So we said last class and kind of the extent to which I want you to understand these models. And well, I'll mention that in a second. So we've got this coefficient for this estimate on the log of height. So what we're thinking about really is, this is really the regression I ran. So I had the log of weight. And I was trying to estimate the relationship, the slope coefficient B, between the log of height and the log of weight. Okay? So we said the way we interpret this is no longer a 1 unit change in the X variable. It's now a 1 percentage change. And a 1% change in the X variable would predict that weight goes up by whatever percent b is, right? So if we look at that model that we ran, that regression output, a 1% change in height predicts that weight goes up by 1.74%. Okay? All right. So I kind of showed you how last class, it takes a little bit of time. We could run through all the different combinations, right? Level, log, level. And remember, the first kind of word is what your y variable is in. Second word is what the x variable is, right? So here we got kind of the output that we ran was a log model. So hopefully if I did it right, it's the exact same numbers here, right? This one that I had labeled log. The p-value, just kind of going over all these things, is 0, which means that we will say it's significant, right? Or that at any level, right, of alpha, we could reject the null. And remember, the null in every single one of these regressions is that slope or that relationship between x and y is 0. Well, we're rejecting that because we found significant enough evidence to suggest that these two things, there is a correlation, right? So we could do the other models. Yeah.
Is the log model the same thing as the Logit model?
The Logit? A Logit model you can think of is when we were talking about the y variable being 0 or 1. Are you thinking about a specific connect question?
Yeah, well, it was the question that I was asking about.
Okay, yeah, so we can double check it. I've got it here. So question 8. So yeah, see, we have this emission variable. We would, this is a little bit of semantics. It's still a regression, but we call it a Logit model, right? Because, that's just the way we specified it, or what we call it if we have a y variable that's 1, 0. I think I mentioned last class, when we have a variable that's 1, 0 as our y, so I guess we can think about the emissions there. I'm guessing they had SAT and something else. Now what this slope coefficient tells you, remember we said if this is either a 1 if they're admitted, 0 if not, it's saying if the SAT score goes up by 1 unit, this is kind of the increase in the probability of being admitted, right? So the interpretation it's very similar. It's the same kind of lane, but it is a little bit different, right? Because it's kind of this change in probability of going from 0 to 1. Because we're talking about being admitted, I can predict what that value is, right? I can come up with, so admission, I can come up with a predicted y value, but the actual y value can never be like 0.5, right? It's either 0 or 1. So, whereas in the other models, when we have a continuous variable, I could see income be 30,239.41, right? I could see that as the actual y variable. Here we can't. All of our predicted y's would never be something we could see unless we get a predicted y of 0 or 1, right? So that's why we kind of why it'll sometimes be referred to as a Logit model. But it really doesn't change what we're doing that much, other than we think about these now as changes in probability of the y variable being 1. Any other questions? Okay. So we can look at these other kind of models we talked about last class. We have different interpretations. The level 1, that's just the kind of normal linear regression that we started out with. So the way we interpret this, a 1 unit change in our x variable. So if height goes up by 1 inch, right? Predicted weight goes up by 4.7 pounds. Okay. Very significant. The p-value is pretty much 0. Okay. We could then do this kind of a level log. Now, sometimes when you think about these models, the log level and the level log, one of them you multiply it by 100, one of them you divide. So we can start to think about kind of maybe even what would make sense, right? So on this one, if I think about, I have the log of height and my y variable is just regular, right? Level, I didn't take the natural log of it. So I now interpret this as not a 1 unit increase, but a 1% increase in my x variable, right? So a 1% increase in height would change the predicted y value by, and I have to remember, I'm either going to kind of take that coefficient and divide it by 100, or in one of these models, I multiply by 100. Well, I can try to, like, even if I can't remember or I can't find where, where I had it written down or where it is in the slides, if I just logically think about this, if I saw someone be 1% taller, right? If I took this coefficient, even if I multiplied it by 100, it'd be really large, right? But even if I didn't multiply it by 100, then this would say that the predicted Y value, the predicted weight would go up by 318. And because I didn't take the natural log of Y, 318 units, if Y is weight, if someone's 1% taller, they would predict their weight be 318 pounds heavier. It doesn't even make sense, right? So I can probably think about this one. Well, this is probably the one where I need to divide by 100, right? Like I probably need to divide that slope coefficient by 100 when I have one of these level log models. So the level log model, maybe we can kind of organize this kind of nice, right? So level, you can kind of think about a 1 unit change in the X variable causes the Y variable to go up by this many units. If I think about my log model, I can think about a 1% change in my X causes Y to go up by this percent. Right? Or if I want to think about it as Y is going to go up by this percent. Right? The one that we just looked at, so that was the level log. We kind of think about, we need to divide this, right? And my X and Y units now, so X was log, Y was level. So it's like a percent change in X causes Y, I guess we could write, come in here, to go up by whatever B is divided by 100 units. Right? And then the last one we have, we can think about, we'll take that slope coefficient, multiply it by 100, but now my X and Y, and I probably shouldn't have wrote X and Y here every single time, but if you want to leave those off, you could. Now my Y variable, I took the log of, so it's a percent change, or it's whatever a unit changes in my X variable causes B times 100% change in my Y variable. So that might help kind of keep a kind of somewhat organized, right, in our mind when we're looking at that. So the last one that we look at is this log level model. Now I can see, just have the level of my X variable, so a 1 unit change in height. So if someone's 1 inch taller, I would predict that their weight changes by whatever this coefficient is times 100, right? So what is that, right? A 1 unit change in height, so 1 inch taller, would predict weight would go up by 2.5%, right? That was where we said log level model, a 1 unit change in X causes Y to go up by B times 100%. So this is how we do the different interpretations of these different models. And this isn't, for the sake of what we're doing in this class, what I told you in the last class is just look at the R squared to kind of see which model best fits this relationship. If we had a little more time, or we're going to be a little more, maybe in advanced stats, we talk a little, there's something a little bit different that we truly would have to do because of these different specifications. But for the sake of what we're doing, we're going to identify kind of which model is correct based off of this kind of R squared, right? Just so we have an understanding of what this R squared is representing to us. It's the percent of the variation that we're explaining in that Y variable. Okay? So I don't know, if we look across these, what, 0.22, 0.20, 0.20, oh, these are close, 0.225 and 0.224. So just barely, right, we would kind of go with the log model here. Okay? Any questions over any of that? Okay with that? Double check here. Okay. So that was a little bit of a review of that. I also want to do a little bit of a review. Some of the slides I didn't get to last week was when we were talking about kind of differences in slope. So I think we didn't get to go over kind of this, wait, we did go over this one, didn't we? With kind of the looks and kind of the effect on wages. So I think this is the example that we did look at, right? So the next one that I wanted to think about, and I think this one, again, throwing a sports example in here, but we can think about just, I think it's another good example of how we can include interaction terms. And I don't know, we're in Indiana, so if you've never seen a basketball game, I find that hard to believe if you grew up here, right? So let's just think about kind of a Logit model here, right? Where we have a Y variable that is a 1 if someone makes a shot and 0 if they don't, right? So we're observing every single shot that was taken, right? Notice we have 392,000 observations. It's a lot of observations. So 1 if the shot was made, 0 if it wasn't. We then kind of think about, well, we know that just physically it's easier to make a shot, shoot a basketball, it's easier to make if you're right next to the rim than if you're 20 feet back, right? So what is that kind of maybe decrease in the probability you make the shot as you move further away from that target? Right? You could do this really for any sport that you're thinking of, right? Maybe even throwing darts. What's the probability I hit a bullseye, right? So we could estimate this relationship, and it looks like it's negative, right? It makes sense, right? P-value is 0, so pretty significant relationship. The interpretation would be if distance here is kind of measured in feet, every time I move back 1 foot from the basket, my probability decreases by 0.009, or really close to 1%, right? About 0.9%. Right? Now, I think I actually had this measured in tenths of a foot. So this is where we have to make sure, I need to know, when I'm looking at the original data, I need to know the units that it's in. So if this wasn't in feet, but instead tenths of a foot, this is actually only the effect of moving back 1/10 of a foot. So if I wanted the effect of moving back an entire foot, and my units are in tenths, I would have to take this coefficient and multiply it by 10, right, to get the effect of kind of moving back 1 foot. So I'll kind of think about this differently, right? So sometimes you might have something and it's not really like necessarily shot made, distance, right? So if this was measured in kind of 1/10 of a foot, B is the impact of moving back 1/10 of a foot or 1/10 of a foot further from the basket. The effect on your kind of making the shot would be whatever B is. But if I want the effect of, say, moving back an entire foot, right? Well, if this is the effect of 1/10 of a foot, the way I get the effect of an entire foot would just be multiply B by 10. If I wanted the effect of moving back 2 feet, well, how many 1/10ths are in 2? I would multiply it by 20. I wanted the effect of 3, multiply it by 30, so on and so forth, right? So just because we have the effect of 1 unit, or whatever unit we're interested in, like finding the effect of, we just kind of multiply by that, right? So if we do that in this model, right? If I move back an entire foot, right? Here's the effect of 1/10 of a foot, so I multiply it by 10. Actually moving back a foot decreases the probability by about 9%. Okay? Might seem a little drastic, but we'll kind of see how maybe this is being driven by some differences across another thing that we're not controlling for. Okay? So let's say I'm thinking about, well, I'm pretty sure that potentially being, a different position in basketball, think about kind of a traditional like 7-footer who doesn't take many shots further from the rim, or potentially guards who are usually more likely to be taking kind of shots and are a little bit better at them. Maybe that's going to impact this estimate, right? So I throw that additional control for the position of the player. I then say, okay, now the effect looks like it's pretty much the same, right? It hasn't really changed much, right? But one thing that's interesting is I'm just controlling for kind of whether or not the player was a guard. What if I think about moving further back from the basket probably impacts a center more than it does a guard, right? And that potentially moving further from the rim isn't as great of an effect kind of for these kind of smaller position players. So really what we're thinking about, and just kind of review when we talk about this with the other example, we're thinking about we have our X variable here, our Y variable here, right? Distance and whether or not the shot was made. Even if kind of they start off with the same intercept, right? It could, well, I forgot we have a negative effect here. Hold on. Let's say, right? as we move kind of further from the basket, maybe our line of best fit looks like this for centers, so it decreases quite a bit. But for guards, maybe that decrease in shot probability isn't as great, right? Maybe there's differences in the slopes. So the way we said when we just included the indicator for whether or not they were a guard, that was just going to shift kind of the intercept. Yeah. Yep. Yeah.
The intercept you start with, is that average of like all your coefficients combined? So like you'd say the center's shot decreases by like 15% per foot, and then the guard's shot would, or percentage would decrease by 5%. But what would the intercept be like?
So it's not going to be the intercept. You don't want to really think about it as an average, right? Because especially once we start throwing in several right-hand side variables, what we're really saying, the only like correct interpretation is if every other variable on the right-hand side is equal to 0, this is kind of the starting point, right? This is the predicted y value. This is where it would start. But the problem is, depending on what your variable is, like if your variable could only be negative values or only be positive, you don't want to think about it quite like an average, right? You just want to think about it, if clean slate, like every other variable is equal to 0, where would this y value be starting? And then as those variables start to move away from that point, we'd be kind of moving, right? As the x variable, here we only have one x variable. So as we move away from that point, what happens to kind of the predicted y?
Because when you add different variables, that intercepts on shifts.
Yeah, and I can't visualize it, right? I can do this because I only included one variable. As soon as I have two variables, I mean, here I can include an indicator and we can still think about it on a 2D plane because I can draw kind of two dimensions as essentially two lines. But let's say I had the shot distance and I also had player height, right? Well, I now have a three-dimensional, I have 3 planes, right? The y variable, but I also have 2 x variables now. And my line of best fit is actually like trying to find the line on this 3-dimension that best fits all the data. And then as soon as I add another one, well, now I have something I can't visualize. It's a 4-dimensional thing where I'm getting this line, I can't put a good visualization to it. But with just the one variable, we can get kind of these nice, think about it as a starting point. And even if we have more variables, like even though we can't like visualize 4 or 5 dimensions, I can think about it as kind of like this starting point. And, as I add dimensions, I'm moving across all the, it's hard to think about anything over 3D, like we can't visualize it. Does that kind of get, okay. Okay, so forget where I was at. Okay, so we want to estimate the differences in these slopes. So we said the way we could do that is add this indicator. The indicator would tell me kind of the shift in the intercept for those guards. And then I would take that indicator for whether they're a guard, multiply it by that x variable I was interested in, and now whatever coefficient is on that interaction term, that will tell me kind of the difference between these slopes, right? So let's do that, right? So I now have this indicator for whether or not they're a guard, which interestingly enough, and I think it had something to do with how this was categorized because it wasn't just guards, there was forwards in there as well. It actually predicted that kind of their intercept was actually a little bit lower, right? But as the shot distance kind of grew, notice now, if I think about for non-guards, as they move back further from the rim, right, 1/10 of a foot predicts that the probability goes down by what, 0.011 or around 1%. But for a guard, it decreases by 0.011 plus 0.003. So for a guard, as they move back further from the rim, the total effect of moving that shot distance would be this coefficient plus the coefficient on the interaction term, right? So for the guard, where is it? It's only going to be about, what, 0.08, right? And I'm multiplying it by 10 here because it's kind of tenths, right? So I can think about here, the additional impact is this 0.003, but to get the total effect for a guard, I had to add this coefficient on the x variable plus kind of the x variable times whatever indicator is for that group I was interested in, right? And in this particular example, the guards, right? So I could think about the effect kind of for a non-guard, or maybe like a center, would be moving back from the rim decreases, by a foot, decreases the shot probably by 11%, but only decreases it by about 8% for these guards. Okay. Any questions on that? Yeah.
Is that because guards are less likely to make the shot? Like, why is the difference?
So it's not that it's that they're more likely, right? Because remember, we're thinking about this effect so as they move back further from the rim, the decrease in the probability they make the shot, right, is actually lower. So let's say I was trying to do a predicted, oops. So you think about it, right? The negative slope isn't as great, right? So the slope here was like negative 0.008. Here it was negative 0.00011, right? So as they move further from the rim, the kind of decrease in the probability of making the shot, it's going to decrease a lot more for the position that's not good at making those shots, right? The centers who aren't as good at making threes.
Oh, okay.
Yeah, it's a little backwards because it's a negative coefficient. It's hard to think about when it's negative, right? Because a smaller negative effect is actually a good thing here, right?
Okay.
Yeah.
Okay, so guards are the ones that make the shots.
Yes. Yes.
Okay, so,
Yep.
okay,
Yeah, and that's what's driving the difference between these two groups is that you have one group for which distance isn't as much of a predictor, right? It doesn't have much of an impact on them. Yeah.
Okay.
In this model, the guard and center variables will either be 1 or 0.
Yeah. So the guard variable, right? When we're doing these differences in groups, it's going to be some measure that's either a 1 or a 0. So it was a 1 if they were a guard or small forward. I think in the data set was how it was kind of stated. They were a guard or a small forward, and then 0 basically if they were like classified as kind of a power forward or a center. Yeah. Any other questions on that? So the real kind of takeaway, this is great. Basketball is fun, but the real takeaway is whenever you want to estimate differences in groups, so here was the original variable I was interested in, the relationship between distance and whether or not they made the shot. I then said, well, there could be differences across these two different groups. So I'll include an identifier, a 1, 0, a dummy variable, and then I'll take that dummy variable and interact it with this x variable I'm interested in, shot distance. Now I have this interaction term. Its coefficient will tell me the difference between the effect of this x variable for guards and non-guards, right? Because it's 0.003. So that was the difference in the effect, but then the total effect kind of for these guards was negative 0.08, right? But the difference in those total effects was whatever that slope coefficient was, beta 3 or B3. Right? Other questions on that? I'll probably do another example of this after Thanksgiving, another interaction example. I have one in here, and after kind of the discussions we've had, this one's kind of tough. So I think I might switch this up to make it a little bit easier because I'm not going to kind of push you guys to go as far as thinking about an example this difficult. I think that's probably what I wanted. Yeah.
Before you didn't add one of the coefficients to something else, but then the other one you did add it to something else. Why did you add the one about the other?
So let's write this whole model out and think about that. So shot made, we've got our intercept, we've got distance, we've got guard, and then this was guard, my spelling's right? Yeah, times distance. Oh, this look weird for some reason. Wait, no, I'm not spelling this right. Right? No, I was. I don't know why it looks weird, probably because my handwriting is terrible. So we have our interaction term here, we have the indicator term here, and we have kind of the x variable that we were interested in. So if we think about the effect for kind of non-guards, and then the effect guards. Right? So for a non-guard, the effect of distance, right, on whether or not they'll make the shot. Well, if they're not a guard, this is a 0, this is a 0, 0 times anything is 0, so none of that has an effect, right? The only effect that distance has on a non-guard is beta 1. For a guard, however, the effect of distance, and I guess I could have written this to be a little more clear, effect of, because I'm saying it, but right, the effect of distance for a non-guard is just beta 1. For a guard, however, these become 1s, and now the effect of distance, well, if distance goes up by 1 unit, this will change, but so will the interaction term, right? If distance goes up by 1 unit, you can think about if I was trying to make predictions, and this went from 2 to 3, well, this will also go from 2 to 3, so I'll get a change from this, but I'll also get a change from this in my predicted y variable. So now the total effect is going to be beta 1 for a guard, but also because this is now 1, I have distance changing here, so a 1 unit change in distance for a guard will now add in beta 3 as well. Right? Because for a guard, this becomes 1, and now a 1 unit change in distance will kind of have this additional beta 3 effect. For a non-guard, this is 0, so the 1 unit change in distance has a 0 effect, right? Because for that group, this would be equal to 0. Is that what you were talking about when I was adding it in for?
I think so, yeah.
For one and not the other.
Beta 0 mean again?
So usually, like in a simple linear regression, if we wrote this kind of not looking at kind of more the academic or statistical way, it's just our intercept or our constant. Yeah. Notice there's no variable associated with it. So I usually would write it as A. I know on the slides I had beta for this example, and we're going to look at a paper that actually kind of writes it. If you looked at like an academic paper, typically they're always going to write it using betas, and beta 0 is kind of like that A. It's always that intercept or constant.
Okay.
Yeah.
Why don't you add beta 2 since it's a guard?
So if we're thinking just about the effect of distance, if distance goes up by 1 unit, what changes here? Nothing. If you were making predictions for what the probability, like a total prediction, right? Here we're just looking at the difference in the effect of distance. But you're right, if I was trying to make predictions, then beta 2 gets added in as well for a guard, but not for a non-guard. Yeah, beta 2 is going to tell us differences in the intercept, right? So like I would start out at beta 0, and then beta 2 is going to be kind of positive, negative, is going to shift where my line starts for guards versus non-guards. And then this was telling me kind of the differences in the slopes. Yeah, it's a lot to, I know it's a lot, but I think hopefully, usually that's, we are interested in kind of maybe the difference in the level, but the difference in the effect is usually what I would say most examples will focus on. Any other questions? These are good questions, so. All right. So everybody else gets the benefit from you guys showing up today, right? Okay, so I put up a PDF on Canvas. Let's go type, because I think, let's see if I can find it. Well, I know I just put it on there this morning. Well, let's just go to Canvas and download it then. Could have sworn I put it on here. So if we go to files, I kind of threw it up there. We'll do the MML on fatalities today. Okay. So I'm going to download this, a little PDF. And we'll think about, actually, I want to take up the whole screen. So let's go downloads. Look at it in this. There we go. So we've got this. This is kind of like an actual publication from a couple economists, Mark Anderson and Daniel Rees. This isn't the final published version of the paper, but it's almost the same thing. So they were kind of looking at medical marijuana laws. This was pretty early on. Let's see. What's the timestamp on this? 2011. So there weren't as many states, but their idea was kind of, are these medical marijuana laws, is there some type of substitution, right? Or potentially complementarities with alcohol consumption, right? If they're complements, this is a bad thing, right? Because if these two things are complements, now potentially more people are using both or using more alcohol. And so now we see traffic fatalities from alcohol-related, traffic accidents go up. But if they're substitutes, and maybe this isn't as impairing on driving, maybe we see an actual decrease, right? So their whole kind of idea is like, we want to know whether or not alcohol and marijuana are potentially, and here we're looking at medical, but or is there potentially some substitutability there? And if there is, do we see these other things? Are we actually like saving lives with these laws, right? I mean, this is traffic fatalities, right? If they go down, this is saving lives. So we're not going to look through the whole paper. This is how I typically look at papers, by the way, to find kind of interesting results. Let me see. I know it's done. Here we go. Usually they will tell you what their regression model is, right? So here we've got the natural log of total traffic fatalities, right? They then have this indicator, and the way they kind of write this ST is saying their observations are a state at a particular year. So they've got like, 30 years, I don't know exactly what it was, 20, 30 years of data. They've got every single state, they've got their traffic fatalities in each one of those years. Right? They then say, okay, in that year, did the state have medical marijuana legalized? Right? So it's a 1 if they did, 0 if not. So we can interpret this beta 1. Notice I told you they write betas in these papers. Beta 1 is the effect of a 1 unit increase here. But remember, when our x variable is a 0 or 1, a 1 unit increase would be like going from not having medical marijuana legalized to having medical marijuana legalized, right? It's going from the 0 to the 1. So the effect of legalizing marijuana on traffic fatalities is beta 1. Yeah.
So is the LN of fatalities, so that's saying every like 1% or it'll increase 1%.
So that's what I was about. So I said the general interpretation, but I didn't say anything about units or percentages, right? Because you're right, we have a log level model, right? So the level changes if I go from being, not having medical marijuana legalized to having it legalized. So in this case, I'm going to have to, multiply whatever my coefficient is by 100, right? Because if we go back here, right, we had a log level model. Remember, we had to multiply whatever coefficient we see by 100. Right? So they present, like when we look at the results, they've actually already kind of put that in there. Okay? So, and then this kind of represents, whenever they bold something here, it's just a shorthand way of saying, we controlled for, this doesn't just represent one other control variable, this represents a ton of other stuff we put in there, right? So they put a bunch of different controls, so like, they had controls for what taxes, alcohol taxes were in those states and years. Let's see, they probably have a longer list if we go down here to the tables. I don't know, no, they don't. They didn't do a good job of, let's see. Let's go back up to their data section. We can get to their data section here. Oh, where is it? Here it is. So they've, I don't know, we could search. It's not overly important. I mean, it is important exactly what they included, but I remember reading this before. They include a bunch of other state characteristics, like in traffic, state level policies on different things. Like I said, they mentioned taxes, speed limits even. So they got all these other control variables. So what we want to focus on is, once they start presenting these, right? Oh, I went a little bit too far. I want to show you the basic results first. I thought it was, yeah, here we go. Oh, here we go. All right, they've got some of these other kind of seatbelt laws, what the blood alcohol content of the person was in the traffic accident. So really what we want to look at is their results, right? So what's the effect? And like I said, they've kind of are presenting these already as kind of the percentage point changes, right? So if the state has medical marijuana legalized, here's the percent change we would expect in kind of the traffic fatalities, right? So in these papers, and we'll look at a few kind of after Thanksgiving as well, they give you the standard error and the coefficient. So if you wanted to, you could find the test statistic, right? Take this coefficient, divide it by the standard error. Once you have that test statistic, identify the correct student t-distribution based off degrees of freedom, which we haven't really talked about, but you could do that, right? Excel always does that for us. But what they kind of do, which is nice, is they actually use these stars to just tell you, like, I'm not going to show you the p-value, but these are the levels at which you could reject, right? So 3 stars means I can reject with 99% confidence, right? When alpha is 0.01. 2 stars, well, we don't have an example in this table, but 2 stars would be the 95%. 1 star is the 90% level, right? So more stars is like stronger evidence of an effect, right? So these are very significant. We can say with 99% confidence that traffic fatalities are decreasing once we have these medical marijuana laws, right? And then they start to include a bunch of different controls. Once you get all the controls in there, they still find it's a smaller effect, right? Because as we add in these omitted variables, it might change our estimate. But once they add in all these effects, we still see a pretty sizable kind of impact, right? So if we go down here, it's kind of interesting to look at, well, how does this vary, right? And so what they did here was they just run this regression, right? And now they're not just looking at all fatalities, they break it down and they run 3 separate regressions. So what was the impact that it had on the Y variable of fatalities, but no alcohol was involved? Well, it looks like maybe there's a decrease, but notice there's no stars here. This is not significant. This is actually not even close to significant, right? So I can't say that there's actually any impact, right? I can't reject the null there. So if I can't reject the null, one of the true values could be that the relationship is what I assumed, 0. But when we look at traffic fatalities with any blood alcohol content above 0, and then blood alcohol content above 0.1, that's where we see the effect exist with 90% confidence. And notice it's larger in size than when we just ran all the fatalities together. So I think it's pretty interesting. They then kind of go on. I'm not going to look at this table. I want to show you this one because this is also kind of an interesting one. Look at the effect for weekdays and during the day. Like I forget where they signified the end of the day was and where night began, but I'm sure it was some hour, that's on average kind of when it gets dark. Notice these are negative, but they're not significant. But look at fatalities on the weekend and at night, which is when you would expect maybe alcohol consumption to be higher. Once you have medical marijuana laws, now you see that's where the decreases in these traffic fatalities exist, right? So, we aren't able to observe kind of the middle effect, but we look here like it would suggest that people are substituting away from alcohol, right? Once medical marijuana is legalized, right? So potentially here, I don't know if you're a big marijuana advocate, you'd be like, yeah, these are saving lives, right? These laws are saving lives by allowing people to kind of use this substance, right? However, if we keep going down, also, you guys see the effects are strongest for ages 20 to 50, which even I think further maybe kind of builds this idea that you're seeing a decrease or kind of a substitution away from alcohol. But I also know that and there wasn't really a slight difference in gender, but that wasn't super interesting. So here was the other one. They then said, okay, we think it's operating through substitution, but we're not sure. So they went out and got some state level beer sales, wine sales, and kind of liquor sales. Now, it doesn't look like anyone's like substituting away from wine and kind of liquor, but for beer, we found those medical marijuana laws, they found these medical marijuana laws actually decreased kind of overall per capita beer sales, right? So this is another thing that might suggest people are substituting away, right? They had some kind of survey response data, which also looked like people were saying they drink less, but I've looked at it. I know what this data looks like, and I believe it, but like the binge drinking kind of not seeing like there's as much going on there. Self-reporting kind of we always have some issues with, but looking at how people actually behave with their dollar, people what they buy, right? It looks like maybe there's a decrease, a substitution away, and that substitution away, right, was kind of like saving lives. So I don't know, I thought there's a pretty interesting paper in it. You know, there's some things they do that we haven't talked about. We couldn't completely, you know, it probably be a little confusing, but at least these kind of basic regressions that they have in here, you know, even with what we've talked about, you can start to like look through these results and then kind of interpret them, right? Notice also, this is very good. Look at their R squared, right? 1 is the highest it can be. They're getting pretty close to explaining a lot of the variation that you see in these fatalities. Okay. Any questions on anything here? Interesting. I mean, at this point, like, I'm showing you more examples that I think are interesting, and it's just getting more interpretation, used to seeing this output. But if you're ever like interested in the example too and have any questions, like feel free to ask. Yeah.
How can Excel possibly tell you how much that you've accounted for all the variables? How does it know?
So remember, would have been in last week's slides. I kind of showed you the math equation for what the R squared is. Where is it? Here we go. So it's this ratio, right? So once you look at this numerator, it's here's my predictions. Here's the deviation from the actual Y value, right? So it's like, how much am I, like, what's the variation in what I'm predicting and what the actual average is? And then look and see, okay, what is the actual deviation of these like the actual Y values? What are their deviations from the average? So on the denominator, I've got this measure of like how much this variable can vary. And on the numerator, I'm saying, I'm explaining, right, based off my prediction, this is how much I think it deviates from the average. So like the ratio of those two is basically like what I'm missing, right? The amount of variation that my predictions is missing out on. Right? And that's where that R squared comes from. Is that, it is hard to think about. I mean, it is harder to think about, like, I mean, when it's coming up with these predictions too, like this is a lot of math behind the scenes, right? Like it's, you know, it's doing it very quickly, but it basically does it using, I don't know, you know, linear algebra with like matrices. So that's why I can do it very, very quick, but it is a little bit harder to think about, but that's where that's coming from. It's like, here's the variation from my predictions from what the actual Y value is. So that's how much of the variation I'm explaining in Y. Here's like the total variation, the actual Y values from that average. Yeah. Any other questions? All right, so we'll just do more linear regression stuff kind of after break. Once again, I'll do the Zoom meetings at 1 o'clock. And if you have any questions in the meantime, feel free to kind of reach out. I'll put an announcement up about those last 2 questions on the Connect assignment as well. Have a safe Thanksgiving and holidays, and I'll be talking to you guys via Zoom on next Monday, a week from today.